Okay, so here we have a 30 kilogram mass on a level surface being acted upon by a 200 Newton force at an angle of 30 degrees. The block accelerates for a distance of 15 meters, and we're given the coefficient of friction as 0.3, so friction is present, and we also have the mass of the block, which is 30 kilograms. So the first thing I'm going to do is I'm going to complete the Freebody diagram for our mass, because we're going to need to be able to see the forces acting on the block clearly. So we have mg acting straight down. We have a normal force because the block is on a surface. So normal force is straight up. And friction is present. So friction is always opposite motion and parallel to the surface. So friction is back like that, and we'll label that friction equals mu Fn. Okay, and then the other thing I want to do is this 200 Newton force is not perfectly x and it's not perfectly y, so in a different color I want to show the components. So this represents the x component of the 200 Newton force, and this represents the y component. Using trig, which I'm not going to show here, the x component is 173.205. 173.205, and I got that just with a cosine. Cosine 30 times 200. And then the y component of the 200 Newton force, we're using sine 30 times 200, and that comes out to be 100 newtons. So we have the x component and the y component of the 200 Newton force. So the first question is, find the work done by the 200 Newton force. So our equation for work is simply force multiplied by distance. And the thing you have to know about this equation is that the force and the distance must be parallel to one another. The force has to be parallel to the direction of motion. So when we're solving for the work done by this 200 Newton force right here, we actually want to be using the component of this force that's parallel to the motion, which is this 173 right here. So the key thing with calculating work done by a force is that the direction of the force must be parallel to the motion. So finding the work done by the 200 Newton force, this would be, to put it completely, it would be cosine 30 times 200 multiplied by the distance that the force acts for, which is 15 meters. So this becomes 173.205 newtons multiplied by 15 meters, which gives an answer of 2,598.0, we'll just round this off to, we'll say 0.76. Not newtons, joules. And this answer is positive. So as we discussed in class, the sign convention for work is very simple. If the force doing the work is in the direction of motion, which this force acting, the 173 Newton force, is in the direction of motion, so it is doing positive work. We would consider this to be positive work, in the direction of motion. Okay, second question, the work done by friction. So that little F there indicates friction. So the work done by friction is going to be negative because friction is always opposite motion, and work done opposite motion is considered to be negative work. So again, we're going to use the equation work equals force times distance, but here the force is friction. It's the frictional force, which we know friction to be mu times normal force. So all I did is, friction is coefficient times normal force, and then we multiply that by distance, and we have work. But the thing we have to solve for is the normal force. We do not yet have this normal force. So the way we find that normal force is by summing the forces in the y direction. So we'll do that right here. So looking at our free body diagram, we have normal force up. We have this y component of the 200, which we know to be 100. So that's this guy right here. And then minus mg. Those are the three vertical forces. And the sum of the forces always equals ma. But there is no vertical acceleration. This block is not accelerating up or down, so we can cross the y acceleration to 0. And now we can take this equation and solve it for normal force. M is 30, G is 9.8. We've already called G negative, so don't plug in negative 9.8. We've already called it negative right there. The normal force comes out as 194. Okay, so now we go back up here. So the work of friction, let's just go ahead and put the negative in right now. Again, the reason it's negative is because friction is opposite motion. Forces that act against the motion are considered to do negative work. So our coefficient is 0.3. I'm just plugging in right here. Our normal force is 194, and the distance that friction acts for is the full 15 meters. All right, so the work done by friction is negative 873 joules. And I should mention we're getting joules here because we have Newton times a meter. A Newton times a meter is a joule. Okay, third question. Actually, third, fourth are very similar. The answer is going to be 0. Okay, so the third question and the fourth question have the same answer. The answer to the third question and the fourth question is that the work done is 0. And the reason for this is because, so for number 3, the work done by the normal force. If you look at the free body diagram, the normal force is perpendicular to the direction of motion. So therefore, it is doing 0 work on the block. And same thing for mg. mg is acting perpendicular to the direction of motion, and forces that act perpendicular to the motion do 0 work. For work to be done, as we said up here in 1 and 2, the force acting has to be parallel to the motion. So we made sure of that in number 1. We made sure of that in number 2. For both of these here, the force and the distance. So take number 1 for example. This force and this distance are parallel to each other. So 3 and 4, the work done by normal force is 0. The work done by gravity is 0. The reason being is that both of those forces are perpendicular to the motion. All right, question 5. Find the net work done, the total work done. Well, we have 2 forces that did work. The 2 forces that did work are the 200 Newton force and friction. So this is going to be work done by the 200 Newton force plus the work done by friction. But the thing we have to remember here is that the work done by friction was negative. So what this looks like is work net equals, so the work done by the 200 Newton force was positive 2,598.076, and then friction is negative, so that's minus 873 because friction is opposite motion. So the net total work done is 1,000 positive 1,725.076. That's the total work done. Now, the fact that our net work came out positive tells us that the block is speeding up. The total work done is in the direction of motion, so there's going to be an acceleration in the direction of motion. Okay, then the last question. Using the work energy theorem. Now the work energy theorem talks about net work. I'm going to erase all this. So the work energy theorem says that the net work done will always be equal to the change in the kinetic energy. And this is kind of a cool equation. So that's going to be kinetic final minus kinetic initial. The initial kinetic energy of the block is 0 because we're told that the block starts from rest, right here. The block starts from rest, so that means the initial kinetic energy is 0. So work net is going to be equal to 1/2 mv final squared. So the final velocity of the block is going to be 2 times the net work over m. And we know that the net work, the total work done, is 1,725.076 joules. And the mass of the block is 30 kilograms. So this gives us a velocity final of 10.72 meters per second. Now, another way you could look at this is with conservation of energy. So I'll just show you one more way to kind of wrap your head around this. We know that mechanical energy initial plus any work done from a non-conservative force. So WNC is work non-conservative. And simply put, a non-conservative force is any force doing work other than gravity or springs. Gravity and springs are the only conservative forces for all of first semester. And this will be equal to mechanical energy final. So the work non-conservative in this problem is this 200 Newton force and friction. Both of those are non-conservative forces because it's not gravity and it's not springs. I'll just leave it at that for right now. So mechanical energy, there's 3 forms. So mechanical energy, we have kinetic, we have potential of gravity, and we have potential of spring. So that's kinetic initial, potential of gravity initial, potential of spring initial, plus work non-conservative equals mechanical final, which is going to be the 3 forms of mechanical energy are kinetic, potential of gravity, and potential of spring. So this is pretty much our conservation of energy equation, which accounts for non-conservative forces being present. So if we look at our situation, at the start of the problem, the block has no kinetic energy, so we can cross this out. The block also has no potential energy, and the reason for that is that the 0 point for this problem is this level surface here. So there's no potential of gravity. And then there's also no springs. There's no spring mentioned at all. So all 3 of these initial mechanical energies go to 0. Now if we go over here to the final point, there is kinetic because the block will be moving. There is no potential of gravity because it's still on the 0 point. H is still 0, and there's still no spring. So what we're left with is work non-conservative is equal to kinetic final, which is the same thing we had up here. So if you follow this through, you get the same answer.